Good morning, everybody. My name is Kiran. I am working as an assistant professor in the department of EEE Anits. I welcome you all to the second part of the lecture on magnetically coupled circuits. In my previous lecture, that is the first part of magnetically coupled circuits, I have discussed regarding Faraday's law of electromagnetic induction and Lenz's law. I have also discussed the difference between self-induced EMF and mutually induced EMF and obtained mathematical expressions for them. I have also discussed regarding self-inductance, mutual inductance and coefficient of coupling and derived the relation between them. In today's lecture, I am going to discuss the concept of dot convention, how to find the electrical equivalent of a magnetically coupled circuits, as well as write KVL equations for magnetically coupled circuits. In my third and fourth part of my lectures on magnetically coupled circuits, I am going to discuss some tutorials based on the concept of dot convention as well as to find equivalent inductance of magnetically coupled circuit. So first, let us see the concept of dot convention. The main purpose of the dot convention is to find the polarity of mutually induced EMF, and that polarity can be found out depending upon the coil orientation and direction of current passing through it. Most of the manufacturers of coupled coils mark one end of each coupled coil by means of a dot, and that dot represents the polarity of mutually induced EMF. Dot rule. So using this dot rule, we can easily draw an electrical equivalent of any magnetically coupled circuit. So dot rule states that in a coupled coil, current entering at the dotted terminal of one coil will induce an EMF in the second coil, which is positive at the dotted end of the second coil. Similarly, the current entering at the undotted terminal of one coil will induce an EMF in the second coil, which is positive at the undotted terminal of the second coil. So in circuits with more than two coils, coupling between various coils generally are denoted by various symbols such as square, circle, triangle and rhombus symbols, etc. So using this dot rule, let us try to learn now how to find electrical equivalent of a magnetically coupled circuit. So before doing that, there are some important points that one should remember. The first one is when the current is changed in one coil, EMF induced in the same coil is called self-induced EMF, whereas the EMF induced in the neighboring coil is called mutually induced EMF. In time domain, the self-induced EMF will be in the mathematical form of L into di by dt, and mutually induced EMF will be in the form of M into di by dt. Whereas in frequency domain, self-induced EMF will be in the form j omega L into I, whereas mutually induced EMF will be in the form of j omega M into I. The third point, that every coil will have only one self-induced EMF, whereas mutually induced EMF can be more than one, and that will depend on the number of magnetically coupled existing with other coils. The fourth point, the polarity of self-induced EMF entirely depends on the direction of current entering the coil, whereas the polarity of mutually induced EMF will depend on the concept of dot convention. So according to this dot convention, that is dot rule, we know that if current enters the dotted terminal of first coil, it will induce an EMF in the second coil, and that positive terminal of this EMF that is induced in the second coil will be at the dotted terminal of the second coil. Similarly, if current enters at undotted terminal of the first coil, it will induce an EMF in the second coil, where the positive terminal of this EMF will be at the undotted terminal of the second coil. So now let us see in detail how to find electrical equivalent of a magnetically coupled circuit. The first case, I have considered this magnetically coupled circuit. Here L1 indicates self-inductance of first coil, L2 indicates the self-inductance of the second coil. I1 is the current flowing in first coil, I2 is the current flowing in second coil. V1 is the voltage existing across first coil, and V2 is the voltage across second coil, and M is the mutual inductance existing between two coils. So here we'll analyze the electrical equivalent of this magnetically coupled circuits in two domains. One is time domain and second one is frequency domain. First, let us see time domain. Here one should remember that every coil will have only one self-induced EMF, whereas the mutually induced EMF entirely depends upon the number of magnetically coupling each coil has with another coil. So since here I have two coils, as you can see, the first coil has one coupling with the second coil and the second coil has one coupling with the first coil. Since each coil has only one coupling with each other, you will have one self-induced EMF and one mutually induced EMF for each coil. The self-induced EMF is generally represented by the coil itself, and mutually induced EMF is generally represented by the rhombus symbol. Here the polarity of self-induced EMF entirely depends upon the current direction. So here every coil will have two ends. As you can see, I1 current is entering at this terminal of the first coil. That is why that top terminal of the first coil is indicated as positive and the below terminal of the first coil is indicated as negative. Similarly, current I2 is entering at the top terminal of the second coil, and therefore the top terminal of the second coil is indicated by positive and the other end of the second coil is indicated as negative. So this is the polarity of self-induced EMF. Coming to mutually induced EMF polarity. Mutually induced EMF polarity will entirely depend upon the dot rule. Now we have to apply dot rule. So here let us consider the current I1. So current I1 is entering at the dotted end of the first coil. So since the current I1 is entering at the dotted end of the first coil, this current will induce a mutually induced EMF in second coil. Now see where the dotted end is located in the second coil. So here we will have positive and here I will have negative. That is, if the current in first coil is entering at the dotted end of the first coil, it will induce an EMF in the second coil, and the positive of that EMF that is induced in the second coil will be at the dotted terminal. So therefore, since the dotted terminal is present at the top end of the second coil, here I will get positive at the top end of the dependent source and negative at the bottom end of the dependent source. Similarly, when I consider current I2, here current I2 is entering at the dotted end of the second coil. Since the current I2 is entering at the dotted end of the second coil, the dotted end in the neighboring coil is located at the top end of the first coil. So therefore, the polarity of mutually induced EMF will be positive at the dotted end and negative at the undotted end. So in this dependent source, I'll get positive here and negative here. So at both the dependent sources, I'll get positive at the top end of the dependent source and negative at the bottom end. So this is what I will get after I apply the dot rule. So now let us write mathematical equations both for self-induced EMF as well as mutually induced EMF. For self-induced EMF, it is L into di by dt, whereas mutually induced EMF, it is M into di by dt. Okay. So if I consider the first coil, the self-induced EMF in the first coil will be L1 di1 by dt, and self-induced EMF in the second coil will be L2 into di2 by dt, because self-induced EMF, as you know, is induced due to its own current. Now the mutually induced EMF is induced due to the neighboring current. That is, I1 will induce EMF in second coil and I2 will induce EMF in first coil. Therefore, the mutually induced EMF in the first coil will be M into dI2 by dt, and mutually induced EMF in the second coil will be M into dI1 by dt. So this is the electrical equivalent of the given magnetically coupled circuit. And now if I apply KVL to first mesh as well as second mesh, will give me the KVL equations. That is, V1 will be equal to L1 dI1 by dt plus M into dI2 by dt. For the second mesh, V2 is equal to L2 dI2 by dt plus M into dI1 by dt. So this is how we find electrical equivalent of a magnetically coupled circuit and write the KVL equation. So now let us see the frequency domain of the same case. So in frequency domain, instead of L1 dI1 by dt, I write j omega L1 into I1. Instead of L2 dI2 by dt, I am writing j omega L2 into I2. Similarly, instead of M dI2 by dt, I will get j omega M into I2, and instead of M dI1 by dt, I will get j omega M into I1. So on applying KVL in the first loop, I will get V1 is equal to j omega L1 into I1 plus j omega M into I2. Similarly, in second loop, V2 will be equal to j omega L2 into I2 plus j omega M into I1. So this is how we apply KVL equations to a magnetically coupled circuit and find electrical equivalent in frequency domain. So now let me consider the remaining cases and find the electrical equivalent as well as KVL equation. The second case, so here the dot placement has changed. The dot in the first coil is located at the top end and dot at the second coil is located at the bottom end. So now let us try to find the electrical equivalent of this magnetically coupled circuit first in time domain. So here also, since each coil will has only one coupling with each other, each coil will have only one self-induced EMF and one mutually induced EMF. Since the current direction has not changed, I1 is entering at the top end of the first coil as well as I2 is also entering at the top end of the second coil. So the positive of the self-induced EMF in both the coils will be at the top end and the other end will have negative polarity. Now coming to mutually induced EMF polarity. So when I consider current I1, in the first coil the I1 current is entering at the dotted end of the first coil. Since it is entering at the dotted end of the first coil, in the second coil wherever the dot is located, the polarity will be positive there and the other end will be negative. Similarly, I2 current is entering at the undotted end. Since I2 current is entering at the undotted end of the second coil, wherever undotted end is located in the neighboring coil, there I will get positive and the other end will be negative. So in the first dependent source, I will get negative at the top and positive at the bottom. In the second coil also negative will be at the top and positive will be at the bottom. So this is the polarity that I will get for mutually induced EMF in this case. The expressions will not change. The same expressions for self-induced EMF as well as mutually induced EMF, that is L into di by dt and M into di by dt. On applying KVL, in this case V1 will give me L1 di1 by dt minus M di2 by dt. Similarly, V2 will give L2 di2 by dt minus M into di1 by dt. The same case in frequency domain will give me Here the polarities will remain same, only the expressions for self-induced EMF will change and will be in the form of j omega L into I, and mutually induced EMF in frequency domain will be in the form of j omega M into I. So since self-induced EMF is due to the same current, here I will get I1 and here I will get I2. The mutually induced EMF is due to neighboring coil, that is why here the current will be I2 and here the current will be I1. On applying KVL, you give me V1 as j omega L1 I1 minus j omega M into I2. The second loop will give me V2 is equal to j omega L2 into I2 minus j omega M into I1. So this was the time domain as well as frequency domain for second case. Since now you got a clear idea of how to find electrical equivalent of a magnetically coupled circuit and writing KVL equation, let me take you quickly through the remaining 6 cases in both time domain as well as frequency domain. So here in time domain, since the current directions have not changed, the polarity of self-induced EMF will be same. Coming to polarity of mutually induced EMF, in the first coil current is entering at the undotted end. So since it is entering at the undotted end, positive will be at the bottom end of the second coil and negative at the top end. I2 current is entering at the dotted end of the second coil. Since the current I2 is entering at the dotted end of the second coil, positive will be at the dotted end of the first coil and negative at the bottom. So the dependent source's polarity will be minus plus minus plus. So the expressions will remain same for self-induced EMF as well as mutually induced EMF. On applying KVL will give me the expressions as shown for V1 as well as V2. Similarly, in frequency domain, I'll get j omega L1 into I1, j omega L2 into I2. The mutually induced EMF will be j omega M into I2 in first coil and j omega M into I1 in the second coil. So these are the KVL equations I will get after applying to both the meshes. The fourth case here in time domain. So here both the dots are located here. The current directions have not changed, so therefore self-induced EMF polarity will remain same. When I consider I1, since I1 is entering at the undotted end, positive will be at the undotted end and negative at the dotted end. I2 is again entering at the undotted end, so the positive will be at the undotted end and negative at the dotted end. So in this case, dependent source polarity will be positive, negative, positive, negative. The expressions for self-induced EMF, mutually induced EMF will remain same, and accordingly we will get the expressions for V1 as well as V2. In frequency domain, only the expressions will change, the polarities will remain same. So V1 as well as V2 will be as shown. So now the fifth case, if we consider, here we can see the current direction I2 has reversed. So since the I1 is entering at this end, self-induced EMF will be positive here and negative here. Since I2 current direction is entering at this end of the coil, so self-induced EMF will be positive here and self-induced EMF will be negative here for second coil. So as obtained in time domain, as you can see, positive, negative, negative, positive. Now coming to mutually induced EMF polarity, in first coil current is entering at the undotted end. So in second coil I will get positive, negative. In second coil, since the current is flowing in this direction, here current is entering at the dotted end. So since current is ending at the dotted end, I will get negative, positive in first coil. So polarities will be minus plus and plus minus. So accordingly, the expressions for self-induced EMF as well as mutually induced EMF will be as shown, and on applying KVL, first loop I'll get L1 di1 by dt minus M di2 by dt. Similarly, if I apply KVL in this direction in the second coil, I'll get V2 is equal to minus L2 di2 by dt plus M into di1 by dt. Similarly, in frequency domain, the polarities will remain same. The expressions for self-induced EMF as well as mutually induced EMF will be as shown. Coming to sixth case, so here the current direction will give me positive negative in the first coil and negative positive in the second coil, since current is entering in this direction in the second coil. So the polarity of mutually induced EMF, in the first coil I1 is entering at the dotted end, which will give me positive negative in the second coil, and here current is entering at the undotted end, which will give me negative positive in the first coil. So the polarity of mutually induced EMF will be negative positive in the first coil and positive negative in the second coil. The expressions for self-induced EMF as well as mutually induced EMF is as shown, and applying KVL to both the loops will give me the following KVL equations. Similarly, in frequency domain, the expressions for self-induced EMF as well as mutually induced EMF as shown. The KVL equations in both the loops are also as shown. Coming to seventh case, in time domain, the polarities of self-induced EMF will be the same as in previous case. Since here current is entering at the dotted end, I will get negative positive in the second coil. Here current is entering in the dotted end. Since current is entering the dotted end, I will get positive negative in the first coil. So the polarities of mutually induced EMF will be positive negative in first coil and negative positive in the second coil. The expressions will remain same for self-induced EMF as well as mutually induced EMF, and then applying KVL to both the loops, I'll get the following expressions. Coming to frequency domain, the polarities will not change, only the expressions for self-induced EMF and mutually induced EMF will change correspondingly. These are the KVL equations. And last, eighth case, in time domain, the polarities will be the same as the previous case of self-induced EMF. In first coil, current is entering at the undotted end. Since it is entering at the undotted end, we'll get positive here, negative here in the second coil. Since in the second coil, current is again entering at the undotted end. So in the first coil, I'll get positive here, negative here. So the polarities will be positive negative and negative positive corresponding in first and second coil. So the expressions for self-induced EMF and mutually induced EMF are as shown, and correspondingly on applying KVL to both the loops will give me the following expressions for V1 as well as V2. So in frequency domain, the expressions for self-induced EMF as well as mutually induced EMF are as shown, and in applying KVL will give me the expressions for V1 and V2 as shown. So these are the 8 basic cases of magnetically coupled circuits, their electrical equivalent and the corresponding KVL equations. So the last theoretical concept in today's lecture is the series and parallel connection of magnetically coupled circuits. So if certain cases that we have studied, the magnetically coupling existing can either be in series connected or in parallel connected. So in such cases, it is possible to replace the entire circuit by a single equivalent inductance. In series or in parallel connection, the mutually induced EMF will have either same polarity or the opposite polarity when compared to that of self-induced EMF. In series connection, if the mutually induced EMF as well as self-induced EMF have the same polarity, then we call it as series aiding. Similarly, when the polarities of mutually induced EMF and self-induced EMF are opposite polarity in series connection, we call it as series opposing. Similarly, in parallel connection, if both the EMFs in polarities are same, we call it as parallel aiding, and if the both EMFs have opposite polarity, we call it as parallel opposing. Now let us derive the expressions for equivalent inductance in all the four cases. So first let us consider series aiding. So if I observe these two circuits carefully, in the first circuit the current is leaving at the dotted terminal in the first coil as well as in the second coil. If I consider the second circuit, the current is entering at the dotted end in both the first coil as well as the second coil. So when the current in a series connection is either entering at both the dotted ends or leaving at both the dotted ends of a series connected coil, then we consider that as series aiding. So now trying to find the electrical equivalent of this circuit, since both the coils have only one coupling with each other, each coil will have one self-induced EMF and one mutually induced EMF. So we know that the self-induced EMF polarity depends upon the current direction. So in first coil, the current is entering at this end. So here I will get positive, here I will get negative. In second coil also, since current is entering at this terminal, I will get positive, negative. So hence the polarity plus minus at plus minus is as shown. The polarities of mutually induced EMF we know depends upon the concept of dot rule. So in first coil, if I consider current is entering at the undotted end, so I will get positive at the undotted end of the second coil and negative at the other coil. Similarly, the current is entering the undotted terminal in the second coil also, so I will get positive at the undotted end of the first coil and negative at the other coil. So in this case the polarities will be plus minus for the dependent source. So in this case, the polarities of mutually induced EMF will be positive, negative, positive, negative. The expressions will be j omega L1 into I in first coil, j omega L2 into I in the second coil, that is the self-induced EMF, and mutually induced EMF will be j omega M into I in first coil and j omega M into I in second coil. On applying KVL will give me the equations to be E is equal to j omega L1 I plus j omega M into I plus j omega L2 into I plus j omega M into I. Taking I common will give me the expression for total equivalent inductance in case of series aiding to be L1 plus L2 plus 2M. Next, let us consider series opposing. So if I observe these two cases, we can see that current is entering at the dotted end in the first coil and leaving at the dotted end of the second coil. Here also the current is leaving at the dotted end of the first coil and entering at the dotted end of the second coil. In either of the cases, we consider that as series opposing. So trying to find the electrical equivalent of this circuit. So the polarities for self-induced EMF will remain same, that is positive, negative, positive, negative. Since current is entering at the dotted terminal of the first coil, wherever dotted is located in the second coil, in this case it is extreme right. So here I will get positive, here I will get negative. In second coil also, here since current is entering at the undotted terminal, here undotted terminal is located in rightmost side, so positive, and here negative. So the polarities for dependent sources here will be negative, positive, negative, positive. We know the expressions for self-induced EMF as well as mutually induced EMF. So on applying KVL, in case of series opposing, you will get the expression for total equivalent inductance to be L1 plus L2 minus 2M. Next, coming to parallel aiding. So here, as you can see, as seen in series aiding, the currents in both the coils should either enter at both the dots or leave at both the dots. So in this case also, every coil will have self-induced EMF as well as mutually induced EMF. If I consider the first coil, current is entering at the dotted end. So dotted end will have positive and negative. Here also current is entering at the dotted end in second coil. So here also mutually induced EMF will be positive and negative. So in this case the polarities will be positive, negative, positive, negative. We know the expressions for self-induced EMF as well as mutually induced EMF. As in previous case, here this current is not same. Since here it is parallel, the currents are I1 and I2 respectively. That is why the expressions will have the terms in I1 and I2. Then applying KVL, or since the three branches are in parallel, I can write E is equal to j omega L1 I1 plus j omega M into I2. I can also write E is equal to j omega L2 I2 plus j omega M into I1. So expressing these equations in matrix form, now my aim is to find the total equivalent inductance of this magnetically coupled circuit, which I can obtain by finding the ratio of total voltage by total current. In this case, total voltage is E and total current is I. And this I is nothing but the sum of I1 plus I2. So in order to find this ratio of E by I first need to find the expressions for I1 and I2. And that I can find by using Cramer's rule. We know the I1 is nothing but delta 1 by delta and I2 is delta 2 by delta. So using the concept of Cramer's rule, find the values of delta, delta 1 as well as delta 2 as shown. So after finding these values, I1 will be nothing but delta 1 by delta, I2 will be nothing but delta 2 by delta. So which will give me the total current I to be I1 plus I2. After finding the total current, from that we'll find the expression for total equivalent inductance, which is the ratio of E by I, and in this case you obtain to be L1 L2 minus M square divided by L1 plus L2 minus 2M. So this is the equivalent inductance in case of parallel AD. And the last case is parallel opposing. So parallel opposing is nothing but in one coil the current should enter the dotted terminal, and in another coil the current should leave the dotted terminal. So here also, after finding the electrical equivalent of this magnetically coupled circuit, we will get the polarities to be minus plus in both the coils. So expressions for self-induced EMF, mutually induced EMF are as shown, and since all the branches are in parallel, E will be equal to j omega L1 I1 minus j omega M into I2. E also will be equal to j omega L2 I2 minus j omega M into I1. Writing these equations in matrix form and finding the ratio of E by I. So in order to find the total current, I must find first the expression for I1 and I2. So finding delta 1 and delta 2 according to Cramer's rule, I'll get the following expressions. So from these expressions, I'll find out the expression for I1 to be delta 1 by delta and I2 to be delta 2 by delta, which will give me the total current I to be I1 plus I2. From that, the ratio of E by I will give me the total equivalent inductance. In this case will be L1 L2 minus M square divided by L1 plus L2 plus 2M. So these are the formulas for the total inductance in case of series aiding opposing as well as parallel aiding and opposing. This ends my second lecture on magnetically coupled circuits. In next lecture, we shall solve some tutorials on the concept of magnetically coupled circuits. Thank you.